Hi everyone, it's Michael. So today I want to go over a theorem that comes up all the time. I think I brought it up on my channel probably at least twice. And it's something I didn't learn it until later in high school, but I wish I learned it earlier because of how often it pops up. So this is the Symmedian theorem, so some of you may have already seen it. But for those of you that haven't, if you'd like to try to solve it, feel free to pause the video. Alright, so now I'm going to go over the solution. So we have a triangle ABC, and the tangents to the circumcircle at B and C meet at point D, and this should be, let E be the midpoint of BC, and we want to show that angle BAD is equal to angle CAE. Alright, so how do we show this? So you can start by noticing that since this is tangent to the circle at B, then angle CBD has to equal angle A, or angle BAC. So basically, we have angle ABC here, and then this angle is equal to angle A. So since the three angles of a triangle add up to 180, the exterior angle would have to actually be the third angle. So I'm actually going to extend lines AB and AC past B and C to points F and G. And then basically we know that angle FBD has to be angle ACB because it's 180 minus these other two angles, and angle DBC is equal to angle A. So I'm going to write this out. Okay, so we have angle FBD, it's 180 minus ABC minus DBC, but DBC is equal to angle BAC. That's because DB is tangent to the circle, and so 180 minus ABC minus BAC, that's angle ACB. And then we can do the same thing with angle GCD, so I'm going to write it out. So similarly, we have angle GCD is equal to angle ABC. So this is kind of interesting. It means that this exterior angle is equal to this angle, and this exterior angle is equal to this other angle. So how do we use that? So I'm going to do something a little bit clever here. So first of all, notice that these are both tangent to the circle, DB and DC, because any two tangents to a circle are equal. So what we can actually do then is we can draw a circle through D, passing through B and C. So I'm going to do that right now. Or I should say a circle centered at D, passing through B and C. And I'm going to let it meet these two lines at two different points. H, I just moved the diagram to make more room, H and I. And the reason, you'll see very soon the reason why I did that. It's because I wanted a triangle that's sort of inversely similar to triangle ABC. And you'll notice that triangle AIH is going to be similar to ABC. And in just a few steps, you'll see why. So first of all, these two triangles BDH and CID are isosceles. So we have angle BHD is equal to angle DBH. And as I said before, angle DBH, well, that's the same as angle FBD, which is angle ACB. And then similarly, we also have angle CID is equal to angle DCI, which is equal to angle ABC. Okay, so it's like, so each of these two angles, angle BHD and angle CID, are basically equal to the opposite angle in triangle ABC. So BHD is equal to ACD, and CID is equal to ABC. And if you look very closely, I claim basically that means that the triangle AHI has to be similar to triangle ABC, and HD and I have to be collinear. So I'm going to write this out a little bit. But basically, since there's 180 degrees in a triangle, the three angles of triangle ABC have to add up to 180. But then also, that means that angle HAI, because that's the same as angle BAC, so angle HAI, angle AHD, and angle AID all have to add up to 180. So basically that means that HD and I have to be collinear. And if you don't see immediately why that would have to be the case, every quadrilateral has to have 360 degrees in it. So if angle HAI, AHI, and AIH add up to 180, or I should say HAI, AHD, and AID add up to 180, then the last thing on that quadrilateral, HDI, has to be 180 also, because they have to add up to 360. So HD and I are collinear, and we also see that triangle ABC has to be similar to triangle AHI, but inversely, due to all these angle equalities I mentioned, because BHD is equal to ACB, and CID is equal to angle ABC. So the two triangles are inversely similar, and not only that, since E was the midpoint of BC, D has to be the midpoint of HI. So since D's, or I guess it's not because, but D is the midpoint of HI because it's the center of the circle, and HI is the diameter. So basically we have two midpoints of the corresponding sides of two similar triangles. So since they're corresponding parts of the two similar triangles, it has to follow that corresponding angles are equal. And so therefore HAD has to equal angle CAE. Okay. But angle HAD is just angle BAD. So I'm going to write this out. So angle BAD is equal to angle HAD. And then since triangle AIH is similar to triangle ABC, HAD has to equal angle CAE, since they're corresponding angles of the two similar triangles, and that solves the problem. So this theorem, like I've said, pops up all the time, and I'm probably going to use it later on. So I hope you all enjoyed this. If you like this video, give it a thumbs up. And if you'd like to see more like this, feel free to subscribe to my channel. Thanks, everyone.